We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars, first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue, since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. Here on planet Earth, we use miles as our standard unit of measurement for long-distance travel. Astronomers measure distances in light years. This is how far light can travel in a year. Just about 6 trillion kilometers. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. In our local universe, M87 dwarfs even Andromeda as the biggest elliptical galaxy. With a diameter of 6 million light-years, IC 1011 is the largest galaxy ever discovered. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous, but why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.8 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble. The light we see from distant galaxies now, however, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies, since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust gas and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source, and our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? In all likelihood, the answer is not yes. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations like the Whirlpool galaxy, then over billions of years develop into more orderly forms, or the Milky Way itself. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes, that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. As it turned out, it was a black hole. And not just any kind of black hole, a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? So observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light-years. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. What then is it that keeps them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky irritated his fellow astronomers because he was so far ahead of his time. And this is a brilliant idea, but he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it, you can't feel it. However, it is likely everywhere. It's a ghostly substance that can go through you without registering your presence. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos, and the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form, and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the two largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The two galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed, and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda, as we know it, will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide, but this age of galactic cannibalism will eventually pass, because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade, and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another, as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, well, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life, according to scientists. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands, since they are the ones who created us and are shaping our identities. Forget everything you thought you knew about the universe. What if a telescope found a signal that could mean life or a galaxy that shouldn't exist? We're not dreaming anymore. The James Webb Space Telescope is rewriting the rules. It's not just looking at stars. It's staring into the past, pulling up data that makes scientists question everything. Galaxies forming before they had time. Planets with chemicals that scream life. Structures too perfect for a chaotic cosmos. This isn't science fiction. It's real, measurable, and it's shaking our understanding to the core. The universe isn't playing by our playbook. It's showing us a cosmic puzzle, and the pieces don't fit. Webb's infrared eyes are catching things we can't ignore. From signals 124 light-years away to galaxies born when the universe was a baby. We're not just finding answers. We're finding questions we didn't know to ask. Today, we're diving into 4 discoveries that turn it all upside down. A planet with a gas that might mean life. A spiral galaxy that looks like home way too early. Auroras on Neptune that don't add up. And galaxies so old they break the timeline. This is the universe talking. And it's not whispering. It's shouting. Stick with us to see what Webb found and why it changes everything. What if a planet 124 light-years away is breathing? The James Webb Telescope found something on K2-18b that's hard to explain. K2-18b isn't just another dot in the sky. It's an exoplanet orbiting a dim red dwarf, sitting in the sweet spot where water could stay liquid. For years, it was just interesting. Too big to be like Earth, too far to make headlines. Then Webb turned its mirror, and everything changed. It scanned the planet's atmosphere, sifting light for chemical clues. What it found stopped scientists cold: dimethyl sulfide. On Earth, this gas comes from life. Tiny ocean creatures like plankton pump it out when they die. It's the smell of salty sea air, sharp and fleeting. Sunlight burns it away fast, so it needs constant replenishing. By life, Webb caught this signal in K2-18b's skies. Not a whisper, but a shout. The levels were high, way higher than Earth's. Think of it like spotting smoke from a fire across the galaxy. You don't know what's burning, but something's alive. This planet has a thick, hydrogen-rich atmosphere, probably cloaking a deep ocean. If life's there, it's not fish or forests. Maybe microbes floating in that alien sea churning chemicals, or something we can't even picture. The signal's strong enough to suggest more than a few specks. It could be an ecosystem, a living world pumping gas on a massive scale. But hold on, science doesn't jump to aliens. There's a catch. Other chemicals like methane can mimic this signal in infrared. Mistakes happen, so they checked again. The signal didn't fade. It got clearer. Stronger, estimated at 1,000 times Earth's levels. That's not a glitch. That's something real. Now, could it be geology, a weird volcano, or gas pocket? Maybe. But on Earth, nothing non-living makes dimethyl sulfide like this. We've looked. No dice. If K2-18b's doing it without life, we need a new rulebook. This is where the cosmic puzzle gets wild. K2-18b isn't some distant theory. It's 124 light-years away, close enough to study, far enough to haunt us. If this is life, we're not talking fossils or dreams. We're talking something alive right now, leaving its mark in the sky. Webb's data is solid, but it's not the final word. More checks are coming. Other telescopes, other teams. They'll rule out every trick, every false alarm. Chemistry, physics. If nothing else fits, we're left with one answer: life. That changes everything. We're not just asking if we're alone. We're measuring what else is out there. What's its chemistry? How does it survive? Is it like us or something stranger? K2-18b's signal is a piece of the puzzle, and it's screaming for attention. We used to think alien life was a future problem, something for starships or science fiction. But now it might be staring us down. A signal from a planet we can almost touch. This isn't the end of the story. It's the start. K2-18b's signal hints at life. But what if the universe built galaxies too perfect for its own rules? What if a galaxy looked like home, but showed up billions of years too early? Webb found one, and it's turning our timeline upside down. Meet Xulong, or Torch Dragon, a spiral galaxy spotted by the James Webb Telescope. It's not just far away. It's far back, shining from when the universe was barely 1 billion years old. That's not long after the Big Bang, when everything was supposed to be a mess. Picture the early cosmos like a stormy sea with gas and stars crashing, merging, tearing apart. Galaxies back then should be chaotic blobs, not orderly spirals like our Milky Way. Spirals need time. Time for gravity to settle, for stars to align into neat arms, for a disk to spin steady. That takes billions of years, or so we thought. Xulong breaks the rules. It's got those arms that balance that structure. It looks like it's been chilling for ages, not freshly born in a cosmic riot. Think of it like finding a polished statue in a quarry, where rocks are still being blasted. It shouldn't be there, but Webb's infrared eyes caught it clear as day. The light we're seeing left Xulong when the universe was a toddler, yet it's already grown up. Its spiral arms are tight, its core is bright, and it's stable. That means it formed even earlier, maybe just a few 100 million years after the Big Bang. Here's the science. We measure this distance with redshift. It's how light stretches as the universe expands, pushing starlight to redder colors. Xulong's redshift puts it at 12.5 billion years away. That's not just a number, it's a problem. Our models say spirals come late after messy galaxies collide and cool. Xulong says otherwise. It's not alone either. Webb's finding more like it, galaxies too neat for their time. This is another piece of the cosmic puzzle, and it's not fitting. Why does this matter? If spirals formed this fast, the universe was cooking way sooner than we thought. Maybe gravity worked harder back then. Maybe dark matter, that invisible glue, pulled stars together like a magnet on steroids. Or maybe our whole timeline's off. Some scientists are rethinking how gas clumped in the early days. Others wonder if the first stars burned out faster, spitting out material for galaxies like Xulong. The wilder idea: the universe's rules might have been different back then. Not by much, but enough to rush things. This isn't just about one galaxy. It's about what's possible. Spirals like Zhulong are stable. They're the kind of places where stars last, where planets form, where life might get a shot. If they were around this early, life-friendly spots could have popped up way before we expected. That's big. It means our Milky Way, our home, isn't so special. It's just one of many, maybe late to the party. Zhulong's telling us the universe didn't waste time. It was building homes while we thought it was still setting up shop. Webb's not done. It keeps spotting these early spirals, each one a jab at what we thought we knew. Zhulong's not an outlier. It's a clue. A clue that the cosmic puzzle has more pieces than we guessed. We're not just looking at a galaxy, we're looking at a universe that's been ahead of us from the start. And that's what makes this so unsettling. The past looks too much like now. Zhulong's early spiral defies the stars, but what's hiding closer in our own cosmic backyard? The James Webb Telescope turned to Neptune, and it's not what we expected. Neptune's the loner of our solar system. Far out, cold, dark, and barely studied. Most of what we know comes from one quick visit by Voyager 2 in 1989. Since then, it's been blurry glimpses through ground telescopes. Nobody thought to point Webb, our deep space champion, at a planet next door. But they did. And what it saw wasn't just pretty lights. It was a puzzle piece that doesn't fit. Webb caught Neptune's auroras glowing at its poles. Not like Earth's northern lights, all soft and shimmery. These are wild, chaotic, driven by forces we don't fully get. Think of it like finding a strange signal on a radio you thought was broken. Something's broadcasting and it's loud. Webb's infrared vision cut through Neptune's haze, mapping heat and chemistry in ways we've never seen. It spotted auroras pulsing with weird patterns, hot spots where there shouldn't be heat, cold patches that defy the sun's weak grip out there. On Earth, auroras come from solar wind-charged particles slamming into our magnetic field. Neptune's got a field too, but it's a mess. Tilted, lopsided, nothing like ours. Those particles take forever to reach it, crawling through space from the sun. Yet Webb saw something else. Temperature swings that don't add up. Some areas cooled too fast. Others burned hotter than they should. It's like Neptune's cooking its own weather and we don't know the recipe. Here's the data. Webb's instruments tuned for distant galaxies picked up chemical shifts in Neptune's atmosphere. Methane absorbs light in weird ways, but something's tweaking it. Maybe magnetic storms, maybe reactions we haven't pinned down. The auroras aren't just a light show. They're clues to a planet we thought we knew. Neptune's magnetic field is a beast twisting in ways that mess with our models. Those hotspots could be energy leaking from inside the planet. Those cold zones, maybe gas sinking in ways we didn't expect. We're not sure. And that's the point. Webb didn't just snap a picture. It raised questions we weren't asking. This isn't about some far-off star. It's right here in our own system. Neptune's been out there keeping quiet while we chased galaxies. Now Webb's showing us we missed something. The sample mentioned Voyager's flyby, but Webb's look is sharper, deeper. It's not just auroras. It's a planet acting alive with storms and heat and chemistry that don't play by our rules. And it's not alone. Uranus-Neptune's twin might be hiding similar tricks. We haven't looked hard enough. Our outer planets are strangers, and Webb's proving it. Why does this matter? It's another crack in the cosmic puzzle. We thought we had our solar system figured out. Earth, Mars, Jupiter done. But Neptune's saying, hold up. There's more. Its auroras hint at forces magnetic, chemical, maybe even geological, that could teach us how planets work. Not just here, but everywhere. If we're wrong about Neptune, what else are we missing? Moons with oceans. Weather we can't predict. This isn't just a pretty view. It's a wake-up call. The universe doesn't stop surprising us even in our own backyard. Webb's not done with Neptune. More observations are coming. Maybe they'll crack the code on those auroras, or maybe they'll dig up new mysteries. Either way, this telescope's rewriting what we thought was settled. It's telling us to look closer, even at the places we thought we knew. Neptune's auroras aren't just lights. They're a signal. Something's going on out there and we're just starting to listen. Neptune's auroras glow with secrets. But what if galaxies formed before they were allowed? The James Webb Telescope found some, and they're breaking every rule. Say hello to JD's GS Z140. It's not just a galaxy, it's a time bomb. Webb spotted it shining when the universe was only 280 million years old. Back then, the cosmos was a hot mess. Gas, swirling stars, barely sparking matter, still figuring itself out. Galaxies weren't supposed to happen yet. They need time. Time for gas to cool, for stars to clump, for gravity to sculpt something solid. Picture it like trying to bake a cake in a microwave that's still warming up. You shouldn't get a cake. But JD's GS Z14-0 is no raw batter. It's a full-on galaxy compact, bright, packed with millions of stars. This is nuts. Our models said galaxies take billions of years to get their act together. First you need stars, tiny ones made of hydrogen and helium burning fast and dying young. They explode, spitting out heavier stuff like carbon. That stuff cools, collapses, forms new stars, and slowly builds galaxies. JD's GS Z14-0 laughs at that. It's got structure, mass, and shine all before the universe even had a chance to stretch its legs. Think of it like finding a skyscraper built before the invention of steel. Webb's got the receipts. It measures this with redshift. JD's GS Z14-0's redshift screams 13.5 billion years old. That's not just far, it's impossible. Or it was. This galaxy's got a mass of 100 million suns squeezed into 500 light-years. It's small but mighty, and it's not alone. Webb's finding more like it galaxies popping up way too early, too bright, too big. This is where the cosmic puzzle cracks open. Something sped things up. Maybe dark matter, that invisible scaffolding, yanked matter together like a cosmic tow truck. Maybe the first stars were giants blowing up fast and seeding galaxies in a hurry. Or maybe the universe's early rules were looser, gravity stronger, time weirder. Scientists are scrambling. Some say gas clouds collapsed faster than we thought. Others think dark matter played a bigger role. The wild ones, they're whispering about new physics stuff we haven't dreamed up yet. Why is this a big deal? These early galaxies aren't just old, they're game changers. If they formed this fast, the universe was ready for business way sooner than we planned. Stable galaxies mean stable stars. Stable stars mean planets. Planets mean chances for life way back when we thought the cosmos was still in diapers. JD's GS Z14-0 isn't just a pretty dot. It's a clue that the universe didn't wait around. It was building fast while we were busy writing rules it doesn't follow. Webb's stacking up these finds, more early galaxies, each one a jab at our timeline. They're not flukes, they're a pattern. The cosmic puzzle keeps growing, and this piece is heavy. It's telling us the universe was never slow. It was always in a rush, spinning out galaxies like it had somewhere to be. And that's what's spooky. We thought we knew the story of the cosmos. But JD's GS Z14-0 says we're reading the wrong book. Webb's not just showing us stars, it's showing us how much we've got to learn. Early galaxies flipped the script. But what does it all mean for us? The James Webb telescopes rewriting our place in the cosmos. Look at what we've found. K218b's got a gas that might mean life pumping out signals we can't ignore. J-Long's spiral showed up way too early, looking like home, before it should. Neptune's auroras are dancing with secrets right in our backyard. And JD's GS Z14-0, that galaxy born too soon, says the universe was in a hurry. These aren't just dots in the sky. They're pieces of a cosmic puzzle, and they're telling us something big. The universe isn't what we thought. It's not slow, not empty, not quiet. It's been busy building galaxies, maybe even life, long before we had a clue. This changes the game. We used to ask if we're alone. Now we're asking how many others are out there. Are we just one piece in a massive puzzle or something special? Webb's data doesn't shout answers. It whispers hints. Galaxies too old. Signals too strong. Lights too weird. Each one's a crack in what we thought we knew. And it's not over. More discoveries are coming. More questions. More pieces. So what now? Keep looking up. The universe is talking, and we're finally listening. Not with dreams, but with hard data. Webb's showing us a cosmos that's alive, restless, and full of surprises. Are we ready to find out what's next? The puzzle's not solved. It's just getting started. Can science fiction become reality? This question isn't just for fans of novels or movies. It's one of humanity's greatest mysteries. The discovery of extraterrestrial life and possibly making first contact would undoubtedly rank as one of the most monumental scientific breakthroughs in history. Yet the universe seems to act like an enormous wall, putting up countless barriers between us and other potential civilizations. Despite these challenges, we continue to search for answers among the stars. Are we truly alone in the cosmos, or is intelligent life waiting somewhere out there, just beyond our reach? The Arecibo message. Our first attempt in 1974. Something incredible happened. At the Arecibo Observatory in Puerto Rico, we sent a powerful radio message deep into space. This wasn't just a casual hello. It was a carefully crafted message packed with information about Earth, our location, basic biology, and even the structure of our DNA. The message was aimed at a star cluster called M13, located about 25,000 light-years away. If there's intelligent life out there, this was our way of saying, "We're here. Are you?" It was humanity's first direct attempt to communicate with a possible alien civilization. But here's the catch: even traveling at the speed of light, that message won't reach its destination for another 25,000 years. And if anyone replies, well, we'll have to wait another 25,000 years to hear back. It's a bold move when you think about it. We're sending out a message with no guarantee that anyone is listening. But it raises the ultimate question: are we really alone in the universe? Is there life out there? So how likely is it that someone or something is out there waiting for our message? The answer seems obvious. Yes. Life on Earth began almost as soon as our planet formed. If it could happen here, why not somewhere else? Astronomer Frank Drake tried to tackle this question with a groundbreaking approach. He created the Drake equation, a formula designed to estimate the number of intelligent civilizations in our galaxy. When the equation was first introduced, scientists projected that there could be about 10,000 civilizations capable of communication. Since then, our understanding of the universe has grown dramatically. For one, we've discovered exoplanets, planets orbiting stars outside our solar system. At last count, astronomers have confirmed over 5,500 exoplanets, and they believe that's just the tip of the iceberg. What's more, scientists now estimate there may be more planets than stars in the cosmos. If the universe is so good at making planets, it stands to reason that it might also create the conditions for life. Even if life is rare, the sheer size of the universe offers countless opportunities for it to exist. The odds seem to favor the idea that intelligent civilizations are out there somewhere. But here's the mystery: if there's so much potential for life, why haven't we found any evidence yet? The vastness of the cosmos. If the universe is brimming with possibilities for life, then why haven't we found anyone yet? One answer might lie in the sheer size of the cosmos. It's hard to wrap our heads around just how vast everything is. Take our own galaxy, the Milky Way. It's so big that even traveling at the speed of light, a signal sent from one end to the other would take 100,000 years to arrive. We're out here in the suburbs of the galaxy, about 75,000 light-years from its edge. That's a long way from any cosmic neighbors. Now think about the Arecibo message. After 45 years, it has only covered a fraction of the distance to its target. At this rate, communication with another civilization becomes a waiting game on a scale we can barely imagine. Even if there are thousands of intelligent civilizations in the galaxy, the distance between us might be so immense that we'll never hear from one another. The laws of physics don't make it easy. Nothing can travel faster than the speed of light. So no matter how advanced we become, those vast distances are a roadblock we can't get around. But that hasn't stopped us from trying. Projects like Breakthrough Listen are using the most advanced technology on Earth to scan the skies. With radio telescopes and optical sensors, they're focusing on the stars and galaxies closest to us, searching for any signs of intelligent life. So far, it's been quiet. like waiting for a call that never comes. But that doesn't mean no one's out there. It just means we're still looking. The patience of the search. Searching for extraterrestrial life is a bit like looking for a needle in a cosmic haystack. Imagine this: even if there are 10,000 intelligent civilizations in the galaxy, there are roughly 250 billion stars out there. That's like trying to find one specific house in a city of 25 million. It's an enormous challenge, and it's going to take time. Even if we do eventually hear something, there's another problem: time itself. Imagine a civilization sends us a signal, but by the time it reaches us, they're already gone. Civilizations rise and fall, and the timeline of the universe is so vast that we might simply be missing each other. Earth has been around for 4.5 billion years, but humans, we've only been here for about 300,000 years. In cosmic terms, we're late to the party. The universe is 13.8 billion years old, meaning other civilizations could have existed billions of years before us. They might have reached incredible technological heights, only to disappear long before we even began searching. But this doesn't mean we should give up. Our search is just getting started. Breakthrough, listen for instance, is focusing on the 1/700 stars nearest to us, using cutting-edge technology to catch even the faintest signal. If there's life out there, projects like these are our best hope of finding it. For now, though, we wait, and in the grand timeline of the universe, patience might be the most important tool we have. The Kardashev scale, measuring civilizations. If intelligent civilizations exist, how advanced could they be? To answer this, scientists use something called the Kardashev scale, which ranks civilizations based on their ability to harness energy. Type 1 civilizations can use all the energy available on their home planet. Type 2 civilizations can harness the energy of their entire solar system. Type 3 civilizations are the ultimate powerhouses capable of using energy from an entire galaxy. And where do we stand? Well, we're not even at Type 1 yet. Humanity is somewhere around Type 0.7, still learning how to fully utilize the energy resources of Earth. But the Kardashev scale offers a glimpse of what might be possible if a civilization survives long enough to keep advancing. Imagine a Type 2 civilization. They might build something like a Dyson sphere, a structure that surrounds a star and captures nearly all of its energy. First proposed by physicist Freeman Dyson, this concept represents technology so advanced it's almost hard to imagine. If such structures exist, they would block most of the star's light, leaving only faint traces of infrared radiation, something we could potentially detect. In 2015, NASA's Wide Field Infrared Survey explorer WISE scanned the skies looking at 100,000 galaxies for signs of these advanced civilizations. But they found nothing. Not a single confirmed Dyson sphere. Does this mean Type 2 or Type 3 civilizations don't exist? Not necessarily. They could be too far away, too rare, or using technology we can't even comprehend. The lack of evidence doesn't mean the universe isn't teeming with life. It just means we haven't found it yet. Are we late to the party? The universe is old, 13.8 billion years old, to be exact. Civilizations could have risen and fallen long before Earth even formed. It's humbling to think that while humans have been here for about 300,000 years, that's just a blink in the timeline of the cosmos. Some scientists believe this might explain why we haven't made contact yet. It's possible that intelligent civilizations existed billions of years ago, but are now long gone. Imagine a message finally reaching us from another world only for us to discover that the senders vanished ages ago. It's like trying to join a party, only to find out it ended before you even got the invitation. But there's another possibility. What if we're the early ones? Earth may seem ancient to us, but in the grand timeline of the universe, we could be among the first intelligent species to emerge. If that's true, it's not just about waiting for others to contact us. It's about deciding what kind of civilization we want to be. Right now, humanity is at a crossroads. We're building the tools to explore the cosmos, but we're still learning how to take care of our own planet. If we ever hope to reach the levels of a Type 1 or Type 2 civilization, we'll need to survive the challenges of today. Our search for extraterrestrial life is about more than just finding aliens. It's about understanding our place in the universe. Whether we're latecomers to the cosmic party or among the first civilizations to emerge, the quest itself is a testament to human curiosity and resilience. Projects like the Breakthrough Listen initiative remind us that even if the universe is vast and the odds seem impossible, we are determined to keep looking. Every discovery from exoplanets to radio signals brings us closer to answering the question, are we alone? But maybe the most important takeaway is this: the universe doesn't owe us answers. The search for intelligent life might take decades, centuries, or even longer. Yet by exploring the cosmos, we're not just searching for others, we're learning about ourselves. Humanity is still in its infancy on the cosmic scale, but we have the tools and the ambition to grow. One day we might become the advanced civilization others are searching for. Until then, we'll keep listening to the stars, sending out our messages, and dreaming of the day we finally hear something back. For billions of years, the universe may have witnessed the rise of countless intelligent civilizations, only to see them obliterated by ruthless filters, from devastating gamma-ray bursts to their own self-destruction. Can Earth overcome the cosmic filters and rise to an advanced civilization? Or will humanity repeat the fate of extraterrestrial civilizations that have vanished in the flow of the universe? If extraterrestrial life exists, the question arises whether their forms and environments would be similar to those on Earth. This idea draws from the concept that certain conditions, whether astrophysical, biological, or societal, act as filters that limit the emergence and longevity of advanced civilizations. Possible filters include cataclysmic events, astrophysical phenomena, or self-destructive behaviors inherent to intelligent societies. If extraterrestrial life exists, its forms and environments might not necessarily resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life make it plausible that extraterrestrial beings might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions. However, these planets are delicate and susceptible to various threats. And this fragility means the universe could filter out intelligent life quickly. One significant threat comes from violent stellar events, such as gamma-ray bursts, which are powerful enough to sterilize planets over vast cosmic distances, potentially affecting entire galaxies. Imagine this: a massive star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, the most powerful explosion since the Big Bang. There are no signs that something catastrophic is about to happen, and then it strikes. The radiation surges, heating the upper atmosphere. Our ozone layer is scorched across the atmosphere. Humans are incinerated by radiation 100 times the lethal dose. As the ozone layer thins, temperatures rise worldwide. This triggers storms, tsunamis, and hurricanes. Most life on land and in water is incinerated. This may sound like science fiction, but if a gamma-ray burst from 100 light-years away struck Earth, it could happen. Even if intelligent species manage to survive these natural occurrences, there is another risk: self-destruction. Drawing from our own experiences on Earth, the development of technology has given us the capability to alter our climate and create weapons of mass destruction. This self-destructive potential poses a serious risk for advanced civilizations. It is plausible that technologically advanced societies may have a brief existence as evidenced by our own history. The short lifespan of advanced civilizations could be a reason why there are so few observable ones at this point in time. The possibility arises that many civilizations may have emerged, but their existence was short-lived due to self-inflicted challenges. This scarcity of long-lasting civilizations could explain the limited opportunities for communication with extraterrestrial beings. Discovering remnants of an extinct alien civilization could serve as a profound warning for humanity. If we were to find evidence of a civilization that destroyed itself through pollution or conflict, it would be akin to looking at our own potential future. This sobering realization could provide valuable lessons for us on Earth, emphasizing the importance of avoiding similar pitfalls. In our quest for understanding the cosmos, we can only hope that some advanced alien species have managed to navigate the challenges posed by the universe's potentially lethal filters, offering a glimpse of long-term survival and prosperity. If we are lucky, there may be an extraterrestrial civilization that will come to visit us in the future. Imagine making contact with aliens. Sounds cool, right? But hold on, are we assuming too much? We tend to think that aliens are just like us, but here's the twist. They're not. We might be imagining them based on what we know about life on Earth, assuming they live on planets like ours. But guess what? Most of the universe might not follow our life and planet rulebook. So could extraterrestrials even survive first contact with us and our planet? July 2019, a satellite on a test mission spotted a new alien world named GJ357d, about 31 light-years away. This super-Earth is over 6 times heavier than our cozy home planet. Now what's a super-Earth? A terrestrial planet, but bulked up with more mass. More mass means more gravity, creating a whole different vibe compared to our Earth. Imagine aliens living on a super-Earth. The gravity there could be super strong. They might not be tall, but I bet they'd be super strong. Super-Earths are just one of the many wild things the universe cooks up. Who knows what other surprises are out there? The possibilities are as vast as the cosmos itself. The universe is a vast playground, with planets of all shapes and sizes, orbiting stars of various types and sizes, forming countless configurations. This diversity opens up a world of possibilities for life that is much richer and more varied than we ever imagined. However, we need to break free from the idea that extraterrestrial life will resemble us. If we're expecting beings with 2 legs like ours, we might as well abandon that notion. The truth is, life out there could be radically different. Consider this scenario: an intelligent alien species in our cosmic neighborhood wants to say hi to us. But here's the catch. If that alien evolved on a super-Earth or circled a red star instead of a yellow one, its biology could be so alien that it might never set foot or tentacle on our planet. Looking at life on Earth, it seems like it's tailor-made for our specific temperature elements and environment. Now imagine an exoplanet with conditions conducive to life. It could still host life forms vastly different from what we're accustomed to. What if an alien world has a bit more potassium, is warmer than our average Earth, or has a thicker atmosphere? Each of these subtle differences could create an entirely distinct ecosystem. So the big question is, can an alien organism truly adapt to our ecosystem when it lands on Earth? It's a cosmic mystery waiting to unfold. Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion held together by a gravitational force so immense it defies comprehension. Yet hidden within this stunning spectacle is an enigma. The visible elements of the galaxy, stars, planets, and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life? Existence and everything in between. The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shaped the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object like a galaxy or cluster of galaxies bends the path of light from a more distant source. This bending creates distorted, magnified, or even multiple images of the background object, much like a glass lens does. When astronomers measure the extent of this lensing, they find something peculiar. The visible mass of the galaxy or cluster is far too small to account for the degree of light bending. The gravitational pull needed to create these effects is immense, far greater than what observable matter could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies. Graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass, extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image and unexpected star velocity is a clue bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction. It is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic, not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible, capturing evidence of dark matter directly. The Large Hadron Collider, smashing particles to unveil mysteries. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data escaping the detectors, without interacting much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters, as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the large underground xenon LUX detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota. LUX relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with a xenon nucleus, it will produce a minuscule flash of light scintillation and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes capable of detecting even the faintest whispers of activity. Although LUX has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, LUX Zeppelin LZ, is even more advanced with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and LUX, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches from cryogenic detectors to bubble chambers to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology, which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs, weakly interacting massive particles, dominate the conversation, other candidates such as axions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter, particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments like the upcoming Lux-Zeppelin LZ detector and advancements in neutrino observatories are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The standard model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions, the electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the standard model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem: the standard model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass-energy content. This discrepancy has placed the standard model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The standard model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only standard model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the standard model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles, like electrons or photons, which are central to the Standard Model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the Standard Model is incomplete. Several theories aim to bridge this gap, including supersymmetry, SUSY. This theoretical framework extends the Standard Model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, LSP, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like axions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics, MOND, challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the Standard Model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the axion, a hypothetical particle much lighter than WIMPs. Axions arise from solutions to theoretical problems in the Standard Model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics, QCD. Unlike WIMPs, axions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes axions fascinating is their potential to form a vast invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments, such as the Axion Dark Matter Experiment, ADMX, aim to detect axions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos, a shadowy variant. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. Primordial black holes, dark matter without particles. A more unconventional candidate for dark matter is primordial black holes, PBHs. Unlike particle-based explanations, PBHs are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun, and might account for at least part of the universe's dark matter. Although PBHs do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether PBHs could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, axions, sterile neutrinos, and primordial black holes, researchers explore other possibilities, including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter, particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while axions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass interaction strength or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past. It also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death, or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter, particles could expose new forces or symmetries in nature, leading to extensions of the Standard Model. Astrophysics understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics forces or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery. It's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter composed of atoms was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this process would have been impossibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull, while dark energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this delicate balance. The tug-of-war, how dark matter and dark energy interact, influences the rate of cosmic expansion. Precise knowledge of dark matter's properties, its density distribution and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe. Whether the cosmos ends in a big freeze, big crunch, or big rip depends largely on the role and behavior of dark matter over cosmic timescales. The lambda cold dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda cold dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background, radiation, and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation. Simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions, small-scale anomalies. The lambda cold dark matter model struggles to explain certain small-scale phenomena like the observed density profiles of dark matter in galaxies. The cusp core problem. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Rionization, the period when the first stars and galaxies began to form. Reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles forces or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs, weakly interacting massive particles. As leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Axions. The discovery of axions would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Axions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift, revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth, force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity, two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider (LHC) are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the Standard Model to include new particles interactions and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass force and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet for all that we've explored, its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the unknown. The universe is far larger, more complex, and more wondrous than we can currently imagine. Dark matter is but one piece of a much larger puzzle, one that includes dark energy, the origins of the universe, and the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge, driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge. It's a source of inspiration. It invites us to dream, to question, and to wonder what lies hidden in the fabric of the universe. What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder. Welcome to our journey into the dark and mysterious world of black holes, the enigmatic powerhouses of the cosmos. Black holes, regions in space where gravity pulls so strongly that not even light can escape, have intrigued scientists and the public alike for decades. In this video, we'll explore what black holes are, how they form, and why they are crucial in understanding the universe. Join us as we dive deep into the science of black holes, uncovering their secrets and the groundbreaking methods used to study them. What is a black hole? A black hole forms when a massive star collapses under its own gravity at the end of its life cycle, squeezing all of its mass into an infinitely small point known as a singularity. Surrounding the singularity is the event horizon, often described as the point of no return. Once anything crosses this boundary, escaping the black hole's gravitational grip becomes impossible. Black holes come with fascinating properties. Firstly, their mass, which can be several times that of our sun, or as massive as millions of suns, when we talk about supermassive black holes at the centers of galaxies. They might also possess spin, rotating at immense speeds and influencing everything in their cosmic neighborhood by twisting space-time itself. Despite their dark nature, black holes are not just cosmic vacuum cleaners. They play a crucial role in the structure and evolution of galaxies, including our own Milky Way. Understanding these mysterious objects not only answers questions about the universe, but also about the fundamental laws of physics. The formation of black holes is a dramatic process, usually stemming from the remnants of a large star that has ended its life in a spectacular supernova explosion. Let's delve into how these mysterious objects come into existence. When a star significantly larger than our Sun exhausts its nuclear fuel, it undergoes a dramatic transformation. Without the outward pressure generated by nuclear fusion to counteract gravity, the star collapses under its own immense gravitational pull. This collapse triggers a supernova, an explosion that outshines entire galaxies and ejects matter into space. For the most massive stars, what remains after this explosion is a core so dense that no known physical forces can stop its collapse, leading to the formation of a black hole. The core effectively collapses to a point of infinite density, a singularity where the laws of physics as we know them no longer seem to apply. But supernova remnants are not the only way black holes can form. In the vast expanse of the universe, black holes can also result from the direct collapse of massive gas clouds under certain conditions, skipping the star phase entirely. This process is thought to contribute to the formation of the supermassive black holes found at the centers of most galaxies, including our own Milky Way. Additionally, when black holes merge, a phenomenon observed through the detection of gravitational waves, they can form larger black holes, further adding to the diversity of these objects in the cosmos. In essence, black holes are born from the death of stars and other high-mass entities, playing a critical role in the cosmic cycle of matter and energy transformation. The detection of black holes. Detecting black holes is a complex task due to their invisible nature. Since no light can escape from them, astronomers must rely on indirect methods to prove their existence and study their properties. One primary method of detecting black holes is through their interaction with nearby matter. In binary systems, where a black hole is paired with a normal star, the black hole can pull in material from its companion. This material forms an accretion disk around the black hole, heating up due to intense gravitational forces and emitting high-energy X-rays before disappearing into the black hole. These X-rays, which can be detected by space-based telescopes, are a telltale sign of the presence of a black hole. Another method involves observing the orbits of stars around an invisible object. In the heart of our Milky Way galaxy, for example, astronomers have charted the orbits of stars around a region called Sagittarius A. The movement of these stars indicates they are orbiting a massive invisible object, confirmed to be a supermassive black hole. Gravitational lensing is also a powerful tool for detecting black holes. This phenomenon occurs when a black hole bends the light from a background object, such as a galaxy or star, due to its extreme gravitational field. This bending causes the light to distort and magnify, appearing as rings or arcs from our viewpoint on Earth. The most recent and groundbreaking method is the detection of gravitational waves, ripples in spacetime caused by some of the most violent and energetic processes in the universe. When two black holes spiral around each other and eventually merge, they emit these waves, which can be detected by facilities like LIGO and Virgo. These observations provide direct evidence of black holes and allow scientists to estimate their masses and other properties. Through these methods, astronomers continue to enhance our understanding of black holes, shedding light on some of the most mysterious objects in the cosmos. Black holes and relativity. Black holes are not only fascinating celestial phenomena, but also crucial elements in the study of Einstein's theory of general relativity. This theory, which revolutionized our understanding of how gravity works, predicts that massive objects can warp the fabric of spacetime, and black holes are extreme examples of this effect. At the core of general relativity is the concept that gravity is not a conventional force, but a curvature of spacetime caused by mass and energy. Black holes, with their immense mass concentrated into an infinitely small point, create profound distortions in spacetime. This is why near a black hole time seems to slow down, and the paths of light and matter are bent, a phenomenon known as gravitational lensing. The Schwarzschild radius, or the event horizon of a black hole, is a direct consequence of relativity. It defines the boundary around the singularity, where the escape velocity equals the speed of light. According to relativity, nothing inside this radius can escape the black hole's gravitational pull, making the event horizon a perfect one-way exit from our observable universe. Black holes also challenge our understanding of spacetime through their singularities points. where the curvatures of space-time become infinite. The laws of physics, as we know them, break down at these singularities, posing significant theoretical challenges and pushing scientists to think about quantum mechanics and gravity in new ways. Observations of black holes thus provide critical tests for the theory of general relativity. Events like the recent imaging of a black hole's shadow by the Event Horizon Telescope and detections of gravitational waves from black hole mergers offer unprecedented insights. These observations not only support the predictions of relativity, but also open new avenues for understanding the fundamental laws that govern our universe. Through their extreme nature, black holes serve as natural laboratories for testing ideas about gravity space-time and the limits of our physical laws, making them indispensable to the field of theoretical physics. Famous black holes and discoveries. Black holes might seem like uniform entities, but they are as varied as the cosmic phenomena that surround them. Some of the most notable black holes have unique stories that have significantly contributed to our understanding of the universe. Cygnus X1. One of the first black holes ever identified, Cygnus X1, became a key subject in the study of these cosmic objects. Discovered in the 1960s as a strong X-ray source, it was later confirmed to be a black hole through its interaction with a companion star. Observations of matter being pulled from the star into Cygnus X1's accretion disk helped astronomers validate the existence of black holes and provided a laboratory for studying extreme gravitational effects. Sagittarius A. At the center of our Milky Way galaxy lies Sagittarius A, a supermassive black hole with about 4 million times the mass of the Sun. Its presence was deduced from the orbits of stars at the galactic center, with their speeds and paths suggesting an extremely massive, invisible object. Sagittarius offers a closer look at the dynamics of black holes at the centers of galaxies and their interactions with nearby stars and gas. M87. The black hole at the center of the M87 galaxy made headlines in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's event horizon, or its shadow. This remarkable achievement not only provided visual evidence of black holes, but also confirmed general relativity's predictions at the edges of one of the most extreme environments in the cosmos. Gravitational wave discoveries. The LIGO and Virgo observatories have detected gravitational waves from several black hole mergers since 2015. These detections are crucial as they provide a new way of observing black holes and testing the limits of our physical theories. Each merger helps astronomers learn more about black hole masses, spins, and the history of galaxies. These iconic black holes and their studies have opened new windows into the high-energy universe, providing crucial insights into gravity space-time and the ultimate fate of massive stars. Unanswered questions and future research. Despite significant advancements in our understanding of black holes, they continue to be sources of profound mysteries and the subject of intense scientific inquiry. Here are some of the unanswered questions and the future research paths that scientists are pursuing to unravel these enigmas. Inside the event horizon, what happens inside a black hole remains one of the biggest questions in physics. Theories suggest that within the event horizon lies the singularity, a point where space and time cease to exist as we know them and where the laws of physics break down. However, the true nature of singularities and what happens to matter as it approaches this point is still speculative. Understanding this could lead to breakthroughs in our comprehension of gravity and quantum mechanics. Information paradox. The black hole. Information paradox poses a significant challenge to theoretical physics. It arises from the contradiction between quantum mechanics, which suggests information is never lost, and general relativity, which implies that information can disappear in a black hole. Resolving this paradox is crucial for a unified theory of quantum gravity, and research in this area is vigorous with concepts like Hawking radiation and firewall hypotheses being explored. Formation and growth of supermassive black holes. The origins and rapid growth of supermassive black holes, especially shortly after the Big Bang, remain unclear. These black holes are millions to billions of times the mass of the Sun and are found at the centers of most large galaxies. Understanding how they formed and grew so massive in a relatively short period of cosmic history is critical for piecing together the evolutionary puzzle of the universe. Future missions and observations. Upcoming missions and observatories promise to shed more light on black holes. The Event Horizon telescope continues to refine its observations to produce more images of black holes. Space missions like the James Webb Space Telescope and the planned Laser Interferometer Space Antenna LISA will explore the early universe and detect gravitational waves from black hole mergers across vast distances, offering new insights into their properties and behavior. Through these and other research initiatives, scientists continue to explore the enigmatic nature of black holes, pushing the boundaries of our knowledge and technology to solve the cosmos's most compelling mysteries. Thank you for joining us on this fascinating journey through the mysterious and powerful realms of black holes. We hope this exploration has sparked your curiosity and expanded your understanding of these cosmic giants. If you enjoyed this video and would like to dive deeper into the wonders of the universe, don't forget to hit the like button and subscribe to our channel for more engaging science content. Your support helps us bring more exciting topics to light. Have any thoughts or questions about black holes? Or is there another cosmic phenomenon you're eager to learn about? Let us know in the comments below. We love hearing from you and are always looking to tailor our content to what you're most curious about. Remember, the universe is vast and full of wonders waiting to be discovered. Stay curious, keep exploring, and until next time, keep looking up.